So integration then. Two reasons why we integrate. One is to solve what's called a differential equation, and all that is something that's got a differential in it. In other words, it's a way of getting back from the differential to the original function, a bit like we did in those little questions we just started off with. And that's called solving a differential equation, undoing that differential. And the other reason why we do it is to find the area underneath the curve, which is what we're going to focus on today. Not particularly focusing on what the value is, what is that area, but what's the formula and what does it tell us. So if, for example, we had something like this, look, dy by dx is 6x, that's the differential. The differential is 6x. So what's the original function? This is a differential equation. So how do I get back to the original function if the differential is 6x, and the terminology I know is a bit awkward to start off with, but remember this means the differential. If the differential is 6x, then the original function y is the integral of 6x. And if you think to the example we just did, what Paul was saying was, what do? I add 1 to the power of x, so if x is 1, I add 1 to get 2, and then divide by the new power, and then tidy up. 6 divided by 2 is 3. So what's the integral of 6x? 3x squared plus this c, this constant of integration. And what we say is we're going to find the integral of 6x with respect to x. So that's how you'd say it. So what we need to do is be able to do this, to be able to integrate it and then find out what that is. And that's what you're going to be asked to do in the assignment. And to do that, you need standard integrals, a bit like the standard differentials that you have. And you've got a copy of the standard integrals in front of you. And just to remind you, let's look at some examples. And you might want to put these on your table of standard integrals. So, for example, let's look at the first one. If I've got something to integrate like this, ax to the n, that's the most common one. And a and n are numbers. So, for example, 4x cubed. So, in that particular example, a is 4 and n is 3. What does the rule tell us to do? We've talked about this already, but here it is stated. We add 1 to the power, so n becomes n plus 1, and then we divide by the new power. So in words, that's what this is saying here. Add 1 to the power and divide by the new power. So what is the power of x, in this case x cubed? Add 1 to the power to get x to the 4, and divide by the new power. So we get 4x to the 4 divided by 4. That's what I've done. Added 1 to the power and divided by the new power. And then you look at it and try and tidy it up. Because the 4's cancel, this becomes just x to the 4. So that would be the answer. And then notice with all of these examples, you add c. So we always add this constant, because when we differentiate, that's disappeared. So when we integrate, it reappears. So every time plus c. If we look at the next example, e to the ax. So let's think of an example. There could be a number in front, but we don't. This isn't in the rule. So let's give an example where the number in the front is there. Say 4e to the 3x. So in this particular example, a is 3. What's the rule tell us? Now, if you think of the differential one, in that one, you're asked to bring the a down, whatever that was, and multiply. So if integration is the opposite, it's not surprising that you bring the a out, and instead of multiplying, you divide by a, or 1 over a. So that's where that rule comes from. So all I do is take the power, 3, and divide by that. So I've got 4 over 3 e to the 3x plus c. Hopefully you can see that. If you don't see it, just say, and we'll have another look at it. No? So the next one, integral of 1 over x is just log x, as simple as that. However, if there's a number in front, so again, let's think of something like 4 over x. Well, we think of that as 4 times 1 over x. So we separate out the 4 and the inverse bit of the function. They are the same. 4 over, sorry, that should be 4 over x, not 4 over 3. We can think of 4 over x as 4 times 1 over x. So in other words, to integrate that, we ignore the 4 effectively, just leave that there. And what's the integral of 1 over x? Log x plus c. So that would become something like that. So the 4 just stays in front. And then we have examples like this sine x here. Again, the a inside comes out and goes underneath, becomes a division, and it changes to a negative. Don't forget that minus sign. So again, let's put a number in front. 3 sine 2x, for example. The 3 would stay, and then I'd integrate the sine 2x, which becomes minus 1 over 2. So the 2 goes underneath, cos 2x plus c. So the 2 goes underneath the 3 effectively. And again, George, if that was just a 1 in front, then it would be 1 over 2.
Whatever number is in front, that's what.
Yes, goes on top effectively, yeah. So if there is no number in front, i.e. it's just 1 times that, then it becomes 1 over 2. Just write down what you think this last one would be. 5 cosine 2x. What would that be? Hopefully 5 over 2 sine 2x plus c. So those are the basic rules. There are other integrals, but they're the main ones that we use, so those are ones I'm giving you. And what we're going to be doing is using this table of integrals exactly the same way as we did the table of differentials. Okay, I'll stop that there.